Let's now proceed with our next topic, which is all about arc length of a polar graph. It says here that let f be a function whose derivatives is continuous on an interval theta is greater than or equal alpha but less than or equal beta. The arc length of the graph of r equals f of theta from theta equals alpha to theta equals beta is arc length is equal to the integral from alpha to beta, the square root of f of theta squared plus f prime of theta squared d theta. We can simplify that to arc length is equal to the integral from alpha to beta square root of r squared plus dr over d theta squared d theta. So we will use this simplified formula to find the arc length of a polar curve. Let's now proceed with the first example. Let's say we are trying to find the arc length of a polar curve with a given radial distance or r is equal to 6 sine theta. So the theta here will serve as the direction of our polar curve. So the first step we're going to do is to find the theta interval. So we have here theta is greater than or equal alpha but less than or equal beta. We're going to find the value of the alpha and the beta. The alpha will serve as the lower limit of our curve while the beta will serve as the upper limit. Let's set the argument of the trigonometric function theta, which is theta is equal to pi over 2. We use pi over 2 because that's the value that only make easier to find points that passes through. So for the curve r is equal to 6 sine theta, that means we're going to set the theta to pi over 2. Next is we put the multiple of theta into the polar curve to find the corresponding values of r. We can use the unit circle as the reference for the values. So for this curve, we have the multiple of pi over 2, which starts from 0 and then pi over 2, and then pi, 3 pi over 2, and lastly 2 pi. So when we plug all these theta values into the polar curve we started with, we will get the corresponding values of r for each curve. And these then will become the polar coordinate points that we can plot to sketch the graph of the polar curve. So for r we have 0 and then 6, we will come back with 0, negative 6, and then 0 again. As you can see, there is a redundancy in the values of r. That means you were just retracing the same sections over and over again. So let's plug here beside the unit circle the values of theta and r that we made through a table. So this point here is our pole. This is the pole of the unit circle. And we also have here the polar axis or the r or radial distance of this unit circle. So based from our table, it starts 0 units from the pole and 6 units from the pole. So the angle 0 units of the pole, but by that we got pi over 2, we're 6 units away from the pole. Then from pi over 2 to pi, the distance from the pole decreases from 6 to 0, which means the polar curve wraps back around the pole, and we're just retracing the same sections over and over again since we have redundant values of r. So we have the lower limit of 0 and upper limit of pi over 2. Let's plug it in here. That means our theta is greater than or equal 0 but less than or equal pi over 2. Now that we have the upper and lower limit or the interval of our polar curve, we can now proceed in getting the interval of this polar curve. Let's now recall the formula of the arc length, and that is arc length is equal to the integral from alpha to beta, the square root of r squared plus dr over d theta squared d theta. So let's plug in the values that we have. We have here the given r, which is equal to 6 sine theta, which is also inside the square root, and we have here the dr over d theta. It's just simply the derivative of our given r, or radial distance. So what's the derivative of 6 sine theta? It will be 6 cosine theta. So we already got the lower limit and upper limit. So the lower limit will be 0 and upper limit will be pi over 2. Let's insert the value of r, which is equal to 6 sine theta. Let's not forget the exponent 2 based from the formula, plus the derivative of r, which is 6 cosine theta. Let's not also forget the exponent 2 here. And then the theta. So we got all the values that we need. Let's first simplify the values inside the square root. (36 sine squared theta) plus 6 times 6, 36 cosine squared theta. Okay, and then the theta. What can you notice inside our square root? We can factor this out. So we have the integral from 0 to pi over 2 square root of 36 times sine squared theta plus cosine squared theta d theta. So you can notice the Pythagorean identity inside our square root, and we can simplify that. So it's just simply integral from 0 to pi over 2 square root of 36 times the Pythagorean identity of these two, which is equal to 1 d theta. And then let's simplify the square root of 36, and we got 6 d theta. So we got the antiderivative of 6 d theta, which is equal to 6 theta, and let's evaluate it from 0 to pi over 2. So that will lead to 6 times pi over 2 minus 6 times 0, and we will just cancel this one, which is equal to 0, and so we got 3 pi. So the arc length of this polar curve is equal to 3 pi. Let's go back to our graph. So the arc length of the polar curve here is equal to 3 pi with a radial distance of 6 sine theta. That's all. Thank you for watching.